All right, hello class. Today we're going to be taking our first foray into actually figuring out which partial sums will, say, converge, or sorry, which series will converge. And that leads us to what's called telescoping series. And we'll get into what that means in just a little bit. But basically, what ends up happening is a series is going to converge basically if the sequence of partial sums converge. So what do we mean by that? Well, let's take a closer look at what we mean by that. All right, so a series, say the infinite sum from k going from 1 to infinity of ak converges if, and it's really an if and only if, the sequence of partial sums Sn, capital Sn, which is just the sum k going from 1 to n of ak converges. Okay, well, what that basically means is the series, right? If you're letting k go from 1 to infinity, as I was saying, the series adds these terms all up. So the series will take a1, and then it adds a2, and then it adds a3, and it adds a4, and it adds a5, and it adds a6, and then a7, and on and on and on and on forever. It'll hit an, and then it'll keep going. Okay, what the partial sums do, well, S1 only gives us a1, then S2 gives us a1 plus a2, then S3 gives us a1 plus a2 plus a3, and S4 gives us a1 plus a2 plus a3 plus a4, and it just goes on and on from there. So then Sn will be a1 plus a2 plus a3 plus all the way up to an, and then it stops. So what this means is that this series, right, the series k going from 1 to infinity of ak is actually equal to the limit as n goes to infinity of Sn. Okay, and so the series converges if and only if Sn converges. Okay, so a lot of times what we do is we take a look at what the partial sums are doing, how they're behaving, and then if they converge, then the series will converge. Okay, before we get really going with these series tests and everything, I do want to bring up the divergence test. Okay, right off the bat, what this says, if the limit as k goes to infinity of ak, if this limit of the ak's does not go to 0, then the series diverges. Okay, so at the very least, this sequence, right, all the terms need to go to 0. If they don't even bother looking at the series because it won't converge. Okay, so this isn't a necessary condition, right? We need a little more, but if we don't satisfy it, then there's nothing left to look at. So for any series, right, k going from 1 to infinity of ak, for it to converge, ak, or the ak's must converge to 0. for that to happen. Or for that not just to happen, for that to even be possible. Okay? For example, if the AKs say converge to 1, well, what happens is this series, it'll be A1 plus A2 plus A3, and it might, be really small for a while, but eventually, you'll get values that are really close to 1. And I'm just going to put approximately a bunch of 1s here. Right, so this is going to be approximately some value, call it W, plus 1 plus 1 plus 1 plus 1 plus 1 infinitely many times. Well, if you add up 1 an infinite number of times, that blows up to infinity. Okay? So the only way it's even possible for a series to converge is the terms need to get really small. If they don't get really close to 0, it's not going to happen. Forget about it. All right, so this is the first test. I wanted to discuss, if you see that the terms themselves don't go to 0, you don't even have to look a step further. All right, so let's take a look at this series here. We want to determine if the series A, which is the series k going from 1 to infinity of 1 over k plus 1 minus 1 over k plus 2, we want to see if this converges. I tend to name my series a letter so I don't have to write this every single time. All right, so to start with, I want to just verify that these terms go to 0, right? 1 over k plus 1 minus 1 over k plus 2, these both do go to 0, right? This goes to 0, this goes to 0 as k goes to infinity. Sorry, that should be plus 2. So this whole thing goes to 0. So it's possible that this series converges. This does not mean it converges. It just tells us it's possible. So it's possible A converges. Okay, that was a terrible G there. Let me fix that up. All right. So now what I want to do is start looking at the partial sums. So let's look at the partial sums. Okay, so we'll start with S1. Well, S1 just takes the first term. It's 1 over k plus 1. So this is, let's make it explicit here. It's going to be 1 plus 1, so that would be 1/2 minus 1/3 for the first term. Now, I'm not going to simplify this right now. It's usually in your best interest not to, and you'll see why as we do this. Okay? So now I'm going to look at K2, which is S2, of course. So that'll be this first term again. All right, so here's k equals 1 term. But then we need to add the k equals 2 term. So the k equals 2 term, we're going to get 1/3 minus 1/4. And this is why I didn't want to simplify this, because here we see that this cancels. The 1/3s cancel, and so we end up with 1/2 minus 1/4. What I want to look at, and this is going to actually save us some time, if we take a step back to what we were just looking at before, Okay. No, the other slide. Here we go. One thing I want to show you is that when we here we go. When we do this, it's sometimes easier, instead of writing it as A1 plus A2, this is actually S1 plus A2. And then here, S3 is S2 plus the next term. And then S4 is S3 plus the next term, right? So it's always the previous S plus the next term. So here, all of this up to this point is S of n minus 1 plus A sub n. Okay, well, how can we use that? Well, we can use that if we scroll back up to what we were looking at. Here, now, instead of doing all the terms over again, like these two again, and then adding the next one, S3 I can just say is S2 plus, and now the k equals 3 term. So it will save us some time to do it this way. So when k is equal to 3, let's bring back our formula again. All right, when k is equal to 3, I'll get 1 over 4 minus 1 over 5. Well, the S2 was this 1/2 minus 1/4, and then we'll add a fourth, and whoops, we'll add a fourth and subtract a fifth. So the fourths cancel. So we get down to 1/2 minus a fifth. All right, then for S4, right, it's going to be S3. So I'll just rewrite that piece. It's 1/2 minus a fifth. So this is S3. Then plus the next term, which is going to be 1/5 minus a sixth. And this is the k equals 4 term. Okay, and once again, these middle terms cancel, and we get 1/2 minus 1/6. So it looks like we have a pattern brewing. I would, without much calculation, suspect that S5 is going to be 1/2 minus 1/7. Because we go 1/2 minus a third, 1/2 minus a fourth, 1/2 minus a fifth, 1/2 minus a sixth, 1/2 minus a seventh. S6 should be 1/2 minus an eighth. And it looks like we could get a pattern for S sub n from this. S sub n will be 1/2 minus 1 over, so what are we doing? 1 goes to 3, 2 goes to 4, 3 goes to 5, 4 goes to 6, 5 goes to 7, 6 goes to 8. We're adding 2. So n should go to n plus 2. Okay, so this is a pattern for the nth partial sum. Let me, there we go. Here we go, the nth partial sum. Now, how that's helpful is now our series, which I called A is the series k going from 1 to infinity, is 1 over k plus 1 minus 1 over k plus 2. Well, we established that this is the limit as n goes to infinity of Sn, right? That is what we established with saying that the series only converges if the sequence converges. And the sequence we just found can be simplified down to 1/2 minus 1 over n plus 2. And as n goes to infinity, this piece goes to 0, and therefore the whole thing goes to 1/2. And there we go. This series A converges. And it doesn't just converge, we know it converges to 1/2. Okay, this is called a telescoping series. And it's called that because at every step, we're basically subtracting part of the previous step. So A is called a telescoping series. Because of the way it behaves. If you write it all out, you get a half minus a third plus a third minus a fourth plus a fourth minus a fifth plus a fifth minus a sixth plus a sixth minus a seventh plus a seventh minus an eighth plus an eighth minus on and on and on. So these terms just all cancel away. So you're essentially getting a bunch of zeros out. Okay, and this eventually goes to 1/2. It's telescoping because you can imagine that you add a value, subtract a value, add a value, subtract, and the things that you're adding and subtracting by get smaller and smaller and smaller. Okay. Okay, so let's look at another example. Okay, so let's take a look at the second series here. Label it B. B is the series k going from 1 to infinity of k plus 1 all over 2k. Well, the first thing we need to look at is what happens as we take the limit as k goes to infinity of k plus 1 over 2k. Well, from our limit rules, we have matching powers of k in the numerator and denominator, so this goes to 1/2, which is not equal to 0. So by the divergence test, B diverges, right? We don't have to do anything else. There's no reason to even look any further. Okay? So that I wanted to show this one just to show how quick the divergence test can help you. If the terms aren't going to 0, you're done. You don't have to do another minute of work on it. Okay, let's consider this series. The series k going from 1 to infinity of 1 over k times k plus 1. So right off the bat, 1 over k times k plus 1, this goes to 0 as k goes to infinity. So there's no worries there. We can do a little bit more work on this. What we'll find, though, is it may be a little tricky to just look at the SNs in this particular form. In fact, it turns out C is actually a telescoping series. It just doesn't look like it yet, right? In fact, what we're going to do is our good friend partial fractions, because if we do partial fractions, okay, we'll find that when we set this up, that this should simplify out to be a telescoping series, right? So we'll have a over k plus b over k plus 1, and then we'll multiply, and have to remember our partial fraction stuff. Okay, and here's a case where we can actually plug in special values. So I'll start by plugging in 0 when k is equal to 0. we get a is equal to 1. Perfect. And if we put k equal to negative 1, we'll get 1 is equal to negative b. So b is equal to negative 1. Okay, so C is actually the series k going from 1 to infinity of, will be 1 over k minus, and that comes from the fact that b is equal to negative 1, minus 1 over k plus 1. And from here, proving that this converges works exactly like the example we looked at before. So this works exactly like the previous example. And I'm saying that because it would be good practice for you to try to see if you can actually get that C converges to 1. Okay, so this would be good practice to try that out. But this is just to show that there are cases where you may have to do a little algebra or some other techniques to get it to be a telescoping series before you're actually able to determine if it converges or diverges. Alright, so for this example, we'll say the series D is equal to the series k equals 1 to infinity of the natural log of k plus 1 all over k. This is also a telescoping series, maybe a little easier to get there than before. Okay, the terms do converge to 0, so k plus 1 all over k, that does go to 1, but remember, natural log of 1 is 0. So the natural log of k plus 1 all over k will go to, let me write it this way, it'll go to ln of 1, which will be 0. All right, so, you know, it doesn't fail the divergence test. We can actually analyze this, and the way we could do it is, as I was saying, a little simpler than the last one. We can just use the log rule where we have the natural log of k plus 1 minus the natural log of k. Here we're using the log rule that if we have division on the inside, we can split it up with subtraction. And then we can start looking at the partial sums. Okay, so for S1, we'll get the natural log of k plus 1, so we'll have the natural log of 2 minus the natural log of 1, so that's actually just 0. Okay, so we just get ln 2. Then S2, well, that will be S1, okay, plus the k term. I'll just write it as the k, or the second term. Okay, so it'll be ln 2. That'll be plus, our k here is 2, so it'll be plus ln 3 minus ln 2. And this ends up being a little weird because what it ends up doing is canceling the outer 2 versus the adjacent 2. Okay, so S2 ends up being ln 3. Okay, then S3, well, that will be S2 plus the third term. Okay, so S2 we found was ln 3. Then the next term, well, k here is 3, so this will be ln 4 minus ln 3. There we go. Then S4 will be S3 plus the fourth term, And I'm sure by now you can actually start seeing a pattern brewing. We got ln 4 for S3. Then we'll add in the fourth term, so our k is 4, so that'll be ln 5 minus ln 4. And we'll get ln 5. All right, and without the calculation, if S4 is ln 5, and let's do it this way. S1 is ln 2, S2 is ln 3, S3 is ln 4, S4 is ln 5, S5 will be ln 6, S6 will be ln 7. Then if we want to find Sn, that will be ln of n plus 1. Now, unlike the previous thing, this does not go to a finite number. The natural log of n plus 1 as n goes to infinity, goes to infinity. So this means, all right, so what, I think we called this D, which is the series k going from 1 to infinity of ln of k plus 1 minus ln of k, ends up being the limit as n goes to infinity, the natural log of n plus 1, which is infinity. So D diverges. Okay, this is an important example because the terms themselves, so this thing here, just this term all by itself, right? That's going to go to 0. However, the terms do not go to 0 fast enough to cause summing them all up to converge to something finite. Okay, so the natural log of k plus 1 over k does not go to 0. Fast enough for the infinite sum to converge, right? It will just get larger and larger and larger and just go to infinity. In fact, that's what most series will do. Most series will likely go to infinity. You have to have very special cases, and it's not just enough for the terms to go to 0. So warning, for the series AK, it's not enough for just the AKs to go to 0. They have to go to 0 really fast. And what I'll say is that the rest of this particular module is finding ways that we can analyze that speed. Okay, so the rest of this module is all tests to determine if the AKs go to 0 fast enough. Okay, so the all we have right now are telescoping series. A natural question is, well, what happens if we don't have a telescoping series? Not every series we come across can be split up and written as a telescoping series. That's a very special case. So, are we lost in that case? And the answer is no. All right, so in the next sections, we will look at tests for series that aren't telescoping. Okay, so I think this is enough of a brain melter for today, and I will catch you all on the next one. Cheers.